Hello everyone, I am Devajyoti, and if you are planning to design a really good anonymous communication protocol, I have a bad news for you. And the bad news is that anonymity always comes with a cost. However, towards the end of this presentation, I might be able to give you some hope. This is a joint work with Sebastian Meiser, Esfandir Mohammadi, and Aniket Kate, which presents the fundamental restriction on anonymous communication networks. So let's see how anonymous communication networks work. Nowadays, we use Zoom a lot. However, there are multiple reports that Zoom misleads its users about a false sense of security and privacy. Suppose Alice is an employee in Zoom and a whistleblower, and she wants to send some company documents to Bob so that Bob can publish it to the whole world. How Zoom misleads its users. However, Alice doesn't want anyone on the internet or even Bob to know her identity. Bob might be paid by Zoom. We are protecting the identity of Alice among all employees of Zoom. Alice is the sender here, and that's why we are calling it sender anonymity. For this talk, we shall focus on sender anonymity only, and there are many protocols which can achieve such property. One prominent example is mixnet kind of protocol. Here, Alice wants to send a message to Bob, but she doesn't send the message directly. Instead, she onion encrypts the message and sends it to through routing nodes 1, 2, and 3. However, routing node 1 waits for a threshold number of messages, and after receiving a threshold number of messages, it forwards the message to node 2. Node 2 does the same, and node 3 forwards the final message to the intended recipients. As long as there is at least one honest node, Alice can achieve anonymity. However, this comes with the cost of latency overhead. Latency overhead in terms of the time node 1 waits to receive the threshold number of messages and the number of hops Alice's messages take to reach Bob. How can you reduce the latency overhead? Node 1 doesn't wait for a threshold number of messages and instead add some dummy messages. However, that introduces bandwidth overhead. As protocol designers, we would love a protocol which provides good anonymity with low latency overhead and low bandwidth overhead. And the research community has actually asked this question for a long time. Can we achieve good anonymity without introducing large latency or bandwidth overhead? And the answer is no, according to our previous paper, which was published earlier. Before going into the specific results, let's define each of the terms more formally. We define sender anonymity using ANOA framework. It is an indistinguishability-based anonymity definition where the evil recipient Eve receives a message from Alice or Bob, and Eve tries to determine who among Alice and Bob sent the message. And we want that the probability that Eve guesses correctly is less than the probability that Eve guesses wrongly with some slack delta. And if the delta is negligible in security parameter eta, then we are calling it strong sender anonymity. Next, we want to define bandwidth overhead and latency overhead. We measure time in terms of communication round, and latency overhead L is the number of rounds a message can be delayed by the protocol before being delivered. For example, here S wants to send a message to R, and S sends the message through four routing nodes. So there are total 5 rounds and 4 additional rounds to for the message to reach R. So the latency overhead L is 4. The protocol here adds 2 noise messages which are marked with red arrows. So the bandwidth overhead beta is the number of noise messages per user per round. That is the dummy message rate. In this case, beta is 2 over 5. We also denote with B the number of noise messages per real message. In this case, B is 2, assuming there are no additional noise messages in the system during that time. Ideally, we want a protocol with strong anonymity, with constant latency overhead and constant bandwidth overhead. With those defined, our previous paper said that When users send messages at the rate of p prime per user per round, to achieve strong anonymity against even a global passive adversary, we need at least the latency times message rate to be greater than half. So this is a parabolic curve which represents the necessary constraint for strong anonymity. Any protocol which is above the curve has hope of providing strong anonymity. Additionally, when the adversary can passively compromise some protocol parties, some nodes, when I say passively compromise, I mean that the adversary can see the internal states of those protocol parties, but the protocol parties still follow the protocol specification. In that case, strong anonymity is impossible with constant latency overhead. Moreover, the protocol needs to follow this second constraint as well. So this was the curve when there are no compromised protocol parties. With compromised protocol parties, the necessary constraint becomes much stricter. So the takeaway from this slide, no strong anonymity with constant latency in the presence of compromised protocol parties. But is it really impossible for protocols to achieve strong anonymity with constant latency overhead when there are compromised nodes present? That doesn't seem right, because we know there are protocols, for example DCNet, that can provide strong anonymity even with constant latency overhead in the presence of compromised nodes. So what was missing in our previous work? We are going to define a general class of techniques which we call user coordination, and the protocol model in the previous work did not assume any out-of-band user coordination. Both the terms out of band and user coordinations are important, which I am going to explain shortly. And there is a wide class of protocols. For example, DCNet kind of protocols, they actually fall out of our previous protocol model. So let's see more closely what this user coordination is. In user coordination, suppose Alice wants to send a message to Eve. However, Alice doesn't work alone. Bob and Charlie also helps Alice. So each one of Alice, Bob and Charlie sends one packet to Eve. Eve can only reconstruct the message from Alice after receiving all three packets. And we are calling those packets shares. However, we are not talking about secret sharing or any specific technique when we talk about user coordination. By user coordination, we mean a class of all techniques that can achieve such effect. And we assume that user coordination can be achieved via pre-setup, and hence the cost of user coordination to be zero. Even with that assumption, it suffers from bandwidth overhead. For example, uh, for each message that Alice wants to send, each one of Alice, Bob, and Charlie sends one packet. So if there are n users, there are n minus one extra messages, sorry, extra packets, and that's a lot of bandwidth overhead. So can we do anything better? Yes, we can we can mix user coordination with other techniques and increase the latency overhead to reduce bandwidth overhead. For example, in this case, Alice, Bob, and Charlie are participating in user coordination, but Devo is daring. He doesn't participate in user coordination. He sends his message as a packet, and all the four packets reaches Eve. Eve can construct a message from Alice only after receiving the three packets from Alice, Bob, and Charlie. However, Devo's packet is independent. Devo can also achieve anonymity if node 2 is honest. However, if node 2 is not honest, Devo can be singled out. I want to mention here that Alice, Bob, and Charlie do not interact with each other in real time, since the user coordination is done as part of pre-setup. If they interact with each other in real time to set up the user coordination, then the user coordination is not really out of band, and the cost of user coordination should be counted. And in that case, we refer to our previous paper for the impossibility bounds. To derive our results, we impose some assumption on user coordination. Our first assumption is that one of the shares is sent by the actual sender Alice. This is because the user coordination happens as part of pre-setup, and at that point the message from Alice is unavailable. So without Alice sending any information about the message, it is not possible to retrieve the message itself. Next, here we see that Bob's blue packet is used to reconstruct the message that is sent to Eve 1, also the message that is sent to Eve 2. And we are saying that is not allowed. So one packet does not take part in the reconstruction of two separate messages. In this case, Bob's blue packet should not be used to reconstruct both message from Alice and message from Charlie. Or we have another assumption, that is mixing is not possible at a compromised node. For example, in this case, if node 2 is compromised, node 2 can always map the input packets to the output packets. With those assumptions, we show that when no nodes are compromised, the necessary constraint for anonymity remains the same. This is kind of trivial because when no nodes are compromised, you can just have a honest third party which can mix the message, except when L equals to 0. When L equals to 0, if you have user coordination, still you can achieve anonymity with a really high bandwidth over it. But is that all we achieve through such fancy user coordination? Not really. We can do better when there are compromised nodes. In the presence of compromised nodes, the protocols with user coordination can do better than protocols without user coordination. For example, if you are not distinguishing between negligible and non-negligible, you are actually looking at the value of anonymity. In that case, definitely user coordination helps. Also, user coordination provides better resistance against compromisation. So let's explain that with a graph. This is the graph for universal necessary constraint. Then this is the curve for when there are no compromised nodes, but without user coordination, the necessary constraint becomes much easier for protocols with user coordination. Let's take some specific examples. For example, when a constant fraction of protocol nodes are compromised. In that case, without user coordination, strong anonymity is impossible if latency is in the order of log eta. However, with user coordination, we derive that strong anonymity is impossible if L square is in the order of log eta. So which gives more scope for protocols with user coordination to achieve strong anonymity. In another example, for any trust systems, there are only constant number of nodes which are honest and most of the nodes are dishonest. In that case, for most of the scenarios, strong anonymity is impossible without user coordination. However, protocols with user coordination in most cases escapes that impossibility. So what are the takeaways from our paper? Our work points protocol designers to focus on protocols with user coordination, at least to achieve resistance against compromission. Still, we cannot do better than the limit specified by the universal necessary constraint, which is 2 times latency times message rate greater or equals to 1. Unless we can break one of the assumptions on user coordination that is specified. Now, what I'm going to give you is some directions where you might find hope. I don't know if you would find hope or not because these are still open research problems and I don't know if they can be solved at all. Our first hope is if we can achieve mixing at a dishonest node. For example, node X doesn't have any idea about the mapping between incoming and outgoing packets. In that case, we can become completely resistant against compromission. However, we still cannot do better than our universal necessary constraint. What else can we do? we can come up with better user coordination techniques. For example, we assume that Bob's blue packet should not be used in reconstruction of two different messages. However, if we can do that, then probably we can do something better than our universal necessary constraint. But we don't yet know any techniques that actually can achieve that, or that can be applied in anonymous communication protocols. As our next step, we are trying to build a protocol which is a hybrid of UC and mixnet techniques. And what are we trying to achieve through that protocol? We are trying to achieve strong anonymity with overhead as close as possible to the necessary constraints that our paper mentions. And we also want adjustable latency and bandwidth overhead trade-off. What do I mean? I mean, depending on the requirement, you can tune low latency or high bandwidth overhead, or low bandwidth, high latency overhead, or medium latency or medium bandwidth overhead. Most of the existing protocols that provide strong anonymity, they are fixed in terms of latency and bandwidth overhead. You cannot really change. But with our new protocol, we want it to be adjustable. And with that, I'll finish my presentation. This is a link to our project page where we can see more details about our project and the paper. Feel free to contact me if you have more questions about the paper or the project or about our future research directions. Thank you for listening to my talk.